Okay, so we just finished some examples of probabilities of random variables. And now we're going to try and graph this. And first we're going to shorten our notation. So instead of saying something like this, or no, here, yeah. Instead of saying something like this, we're going to shorten it to the probability of 2. So the probability of 2 means the probability that the random variable x takes on the value 2. And if we want to be general and not talk about 2, but the probability that x equals some number, then we'll just call it little x. Okay, so we'll say the probability that x equals some number little x, right, instead of 2 or 0 or 1 or 10 or whatever, and we'll shorten that to the probability of little x. So we'll write it like this. So instead of writing the probability that x equals 2 like this, we'll say little p of 2. And if we just want to be general and say the probability that x equals some little x, some particular value, we'll write that like this, p of x. So we're going to start out with that. So given a random variable x, we are interested in the probability that x takes on a particular real value little x. Like here it's 2, like here it's 0. In example 5, we see that x takes on the values 0, 1, 2, 3, whatever. We now represent the probability that x takes on a real value, x, by little p of x. And little p of x is called the probability function of the random variable x. So we have a random variable, and associated with that, we have probabilities, right? With each value that the random variable can take, there's a certain probability. We've been doing that over and over again in the last examples. So, like back here, with each of the values that x could take, here this was for the 2 dice, x could take the value 2, x could take the value 3, the sum of the dice. X could take the value 4, x could take the value 7, x could take the value 12, right? Which, with each value that x can take, we're assigning with probability a probability to that value that x can take. So for those of you that like to picture it this way, we said that x was like a kind of a function that assigns with each element in the sample space to a number, and that can be any real number. And now we're saying this thing, the probability of x, that's p of little x, is now a function which takes values from this space, which is x can be basically anything in R, in the real numbers, any real number, and assigns it to values over here, which have to be numbers, since they're probabilities, they have to be numbers between 0 and 1. So we can view it as two functions. So first we use x to go from the sample space to R, and now we're using p to go from R to all the numbers between 0 and 1. So anyway, little p of x is called the probability function of the random variable x. Okay, now they say we can describe the various probabilities of x geometrically. In other words, we can just make a picture, a graph of it. Okay, so let's go back to tossing 3 coins again, 3 fair coins, and let x again denote the total number of heads tossed. So again, x, table 4 summarizes the results already obtained in terms of the values of little x. Now we're using little x. Okay, but it's the same thing. So little x could be 0, little x could be 1, little x can be 2, and little x can be 3. When you toss 3 coins, you can get at most 3 heads. And these are now we have the probability function of x, which is 1/8 the chances for that, 3/8 the chances for this, 3/8 chances for this, and 1/8 the chance for this. So now we can consider graphing this function, right? X and p of x, that looks like something we might try and graph. They say the points are 0, 1/8, 1, 3/8, 2, 3/8, 3, 1/8. So we can, of course, graph it either this way or this way in the Cartesian coordinate system. That's the xy axis. We could also graph it this way or this way. Still 1/8, 3/8, 3/8, 1/8, or this way. So for any of these, we can see by looking at the graph that we sort of have a kind of symmetrical curve here. We could say a symmetrical probability distribution. And it has a kind of peak in the center. So one, they say, is a line graph, or sorry, one of them was a line graph. We had a bar graph. And this last one they refer to calling it a histogram. So this is called a bar graph. This also looks like a bar graph. But this type is called a histogram, and we're going to think about that later. They say a histogram is a bar graph with touching bars having equal bases. So the widths of the bases are all the same, right? What's the width of this base? It's from 1/2 to 1.5. What's the width of this base? From 1.5 to 2.5, and so on. Those are, when we have those characteristics, we call it a bar graph. Except in addition, we need when a histogram is used to represent probability data where the random variable x takes on integer values. Oh, sorry. They say, sorry. In particular, when a histogram is used to represent probability data where the random variable x takes on integer values. So what does that mean? That means that the values that on the x-axis are integers only. Each bar has its base centered at x equals k. So x equals 1. The centers are here. The integer values are the centers. With width equal to 1 and height equal to the probability. So in other words, what's the height of this bar? It's 3/8, which was the probability of getting a 1. What's the height of this bar? It's 3/8, which was the height of which was the probability of getting x equals 2 heads, actually. Now they also say, note that in this case, the probability that x equals k equals the area of the rectangle. It just sort of happens to be that way, right? So what's the probability that x equals 2? It was 3/8. What's the area of this rectangle? Because the width is 1, right? Then 1 times the height gives you 3/8, which, so the area of this is also equal to the probability that x equals 2, right? The area of this one is, the width is again just 1 because the way we're drawing it, and the height is 1/8, which was the probability. So 1 times the 1/8. So in addition to the fact that the height is equal to the probability that x equals 3, the area is also equal to the probability that x equals 3. And he says, they say, this property is extremely useful in section 9.6. Okay, so example 8 says, graph the probability function of the random variable x in example 7 using the 4 types of graphs mentioned. So this was about the defective transistors, and we figured out that you could get 0 defective, 1 defective, or 2. And those are the different values of x, and the probabilities associated with those we figured out were this, this, and this. So if that's true, let's make the graph. So what's the graph look like? We can do it with the dots. So 0 was much more likely, and these two were equally likely but very low. We could also draw it with the dots, but with the lines connecting the dots. We could also draw the histogram, the bar chart, bar graph, or the histogram. Now notice the histogram again. The width of the bars is 1. So that means that the height and the area both give you the same thing. So you can read the probability by looking at the height, just like you can here, but you can also read the probability by looking at the area. Okay, that's the end of this section. So take a look at some of these problems, and then we'll go on to something in 9.2 called the expected value of a random variable, which really has to do with, is kind of like talking about the average or the mean for the random variable. What's the typical, most likely, not exactly most likely, but what's the typical value for x? So what's the most typical sum of the die that you're going to get when you roll 2 dice, and so on. Those kinds of questions, we'll go to that next.